Hi everyone, welcome to Bits and Brains. So today we are going to learn about AVL tree rotations. And trust me, by the end of this video, you will never look at a tree the same way again. So first off, imagine you have a scale, and on one side you put 3 books, and on the other side you only put 1 book. The scale tilts, right? Now imagine this scale is your computer storing data. Well, if it is too much, your computer becomes slow. Like really slow. That's exactly what happens inside a normal binary search tree when we insert data in a wrong order. But what is this AVL trees? So they are like smart organizers. They don't let the scale tilt too much. They fix it immediately using something called rotations. So in this video, we are going to explore what imbalance means and what shapes cause it. And of course, 4 types of rotation as well as the actual Java code behind it. So let's begin this journey of balancing the digital scales. Now first, let's talk about binary search trees or else BST. So a BST follows 3 golden rules. And the first one is left is smaller than parent. And the second one is right is bigger than parent. And the third one, not duplicates. So imagine we are inserting numbers such as 30, 20, and 10. So we follow the rule and get this kind of answer. This is a correct BST, but look at it. It's like falling a tower. This is what we call unbalanced. And here's the problem. A tree like this makes searching slow. And instead of jumping like a monkey from branch to branch, we have to climb one by one, like a little snail. That's why we need a smarter tree, the AVL tree. Before jumping into rotations, we must learn 2 things. They are node height and balance factors. So, height is the number of edges to the deepest leaf. A leaf node has height 0. So, let me show you guys an example. So, as you can see, 2 is a leaf and the height of it is 0. So, now we have to find the balance factor. So, to find this balance factor, we have to use this scale meter, which is balance factor is equals to height left minus height right. So the scale is balanced if answer is only -1, 0 or 1. An AVL tree is just like a BST but with one superpower. It self-balances itself after every insertion or deletion so that BF is always -1, 0 or else 1. It never becomes a long chain, never leans too much, and always gives reliable search performances. It's like the tree version of a personal trainer, keeping everything in shape. Before we rotate, we must understand the shape the nodes formed when imbalance happened. These shapes are called topologies. So first let's talk about the first topology, the straight leg. These nodes are arranged in a straight line, either entirely to the left or entirely to the right. This often leads to single rotation. And the second topology is dogleg. Nodes from a single zigzag pattern, meaning a left-right or right-left configuration. These require double rotations. And the last, spider leg. Many bends before imbalance. It's more of a concept to show imbalance can happen deep inside, but we still fix it locally using a double rotation. Now let's see the 4 ways a tree screams for help. The first one is right, also known as RR. And the second one is left, also known as LL. And the third one is left, also known as LR. And the last one is right, also known as RL. Now let's talk about what are these one by one. To understand this method easily, let's first imagine every rotation happens around 3 nodes. The first one is letter A, and We can call it the unbalanced node, where the problem starts. And the second one is B, child of A, the middle node that helps fix the balance. And the third one is C, grandchild of A, the last inserted node that caused the imbalance. So when I say a rotation case like RR or LL, it always means the path we travel from A, B, C when inserting the new value. Okay, now let's move on to the first topic, RR case. So this imbalance happens because the new node was inserted into the right subtree of A's right child, just like this. See, A's right side kept growing, A to B to C, like a straight slide leaning right. To make things right, what we need to do? So B comes up to replace A, and A moves down to the left. And lastly, C stays on the right. This keeps the BST rule correct and balance the scale. Now let's move on to the second topic, LL case. This imbalance happens because the new node was inserted into the left subtree of A's left child, just like this. This time the left side kept growing, A to B to C, the straight four leaning left. So what do we need to do? First, B comes up, and then A goes down to the right. And lastly, C stays on the left, balanced again. The third case, LR case. The new node C was inserted into the right subtree of A's left child, just like this. So now this isn't straight, it has a bend, like an elbow. That's why we call this a dog leg shape. So what do we need to do? Rotation at B removes the bend and turning it to LL shape. And then we fix the bend first. Then balanced A. Lastly, C becomes the new root. Now the tree is perfectly balanced and BST rule still holds. Okay, finally to our last case, RL case. The new node C was inserted into the left subtree of A's right child, just like this. This is also a dog leg but bending the opposite way. So what do we need to do? Rotation at B fixes the bend and converts it into RR shape, just like this. And then fix the bend at B first. Then balance A and C becomes a new root. Just like that, we balance that again. To summarize this up, think of it like this. Straightforward, a one rotation saves all. Got a bend? Well, fix the child first, then the parent. And remember, the grandchild always becomes the hero and comes to the top of double rotation. And that's how AVL trees heal themselves and stay balanced, fast and also smart. Alright, now we are entering to the main part of AVL trees, the code. Don't panic when you see this. I'll explain it like a recipe, step by step, so anyone can understand. So here, the first line. This is the function name. It says rotate this node to the left when it is unbalanced. And the second line, AVL node new root equals to node right, which means step 1 in our recipe. Take A's right child and call it new root because after rotation this node will move up. And the third line, keep B's left subtree aside safely. We named it temp. Why? Because we don't want to lose that part of the tree while swapping nodes. Then new root left equals to node. It means attach A as the left child of B. This is like saying B is now the new parent. A becomes its left branch. Node right equals to temp. Take the stored subtree and reattach it to A's right side. So nothing get lost, everything stayed connected. And then update heights of both nodes because the tree shapes change. Height is important to check the balance again later. Final step. Return B because it becomes a new root of this rotated part of the tree. So in simple words, left rotation means B comes up, A goes left, subtree reconnects to A, height update. Lastly, balance subtree returns B as new root, like recognizing weight on a scale. Okay, now to the right rotation code. In this code, the first line, this function fixes left-left imbalance by rotating the node to the right. And the second line, we take A's left child and call it new root because it will move up. Then store B's right subtree safely as temp so we don't lose it. And then new root right equals to node, which means make A the right child of B. Now B is the parent, A becomes the right branch. And then reconnect the stored subtree to A's left. After that, update height because the tree structure changed. Finally, return B because it became the root of the rotated subtree. So, lastly, right rotation means R comes up, A goes right, subtree reconnects to A, height update. Lastly, balance subtree returns B as new root, like shifting books from left side to right side of a track to stop it from falling. Okay, now let's move on to double rotation explanation. The first one is left-right rotation. Here, Y is unbalanced node. So, the first thing we need to do is rotate B to left and then remove the bed. Then rotate A to right to fully balance. And finally, return the new root. It's like fixing a bent straw. First, straighten the straw, then flip it into position. Remember, you don't need to memorize the code to understand AVL rotation. Just remember the purpose of each step. So, whenever your tree becomes unbalanced, these rotations run behind the scenes like a smart mechanic fixing a car alignment. Yes, you don't see the engine working, but it keeps the ride smooth. I think now you can see, just like balancing a real scale, AVL trees balance data so your program runs fast, smooth and reliable every time. So if this video helped you to understand AVL rotation, drop a like, subscribe and comment below. Thank you for joining with Bits and Brains. And I'm hoping to see you guys in our next video with another interesting topic.